you'd have to decline.
Thomas, stop being helpful.
Okay, so welcome everyone to another complex system seminar. I think they can hear me even.
Yeah, it's just that the TV to mute while you're talking.
Okay.
Because you don't do your microphone coming out of this speaker.
Okay, so thanks everyone for coming.
Why is it switch on automatically? Sorry.
Sorry, we're just adjusting something here.
Just let Thomas introduce himself.
Okay.
Yeah. Go, Thomas, you're talking.
Okay, so hello everybody. Oh, that's cool. I don't hear my own echo. And welcome to my presentation on consistency in dynamical systems. That's a topic that had been bothering me for quite a few years and seems to be slowly wrapping up now. So I'm going to involve you in this review. I'm first going to talk about the relationship between that weird thing called consistency and conditional stability. Then some time series analysis for multivariate time series, and finally reservoir computing, where actually the last 2 points are not really in that order, so to say. They're connected, and yeah, it also, sorry, who's there?
Let's just make this.
Okay. Yeah, actually, I'm covering a lot of topic areas here, both from experimental, numerical, and analytical, and different disciplines. And yeah, like the title, consistency, I'm going to try to make all of this actually consistent. We're going to first start with a very simple example. The autonomous dynamical system, so that's something that you all might know. It's a bunch of initial conditions as an ensemble of trajectories plotted here. You see the butterfly effect. But how does that look like if you have a driven dynamical system? No? Eventually, it looks exactly the same if that system is unstable. But something that you might not be used to is the inverse situation, namely conditional stability. When you have a driving signal that actually causes the oscillations, but a widespread ensemble of initial conditions converges then to all the same response. Now that something that I highlighted here, sorry Thomas for the colors, that's an old figure that I hadn't been able to adapt, but there's some limit trajectory that is being then approximated by all members of all units of this ensemble. And that's something that we like to characterize. For the autonomous system, we have a set of Lyapunov exponents. We know that the maximum Lyapunov exponent is going hand in hand with the dynamics. You have a stable fixed point for a negative one. You have chaos for a positive one, and something in between. Could be periodic, quasi-periodic, or if you have more complex systems, also critical behavior. All sorts of interesting stuff going on here at this transition. That's more or less the entire picture. Now, what's the corresponding thing in the driven case? Well, let's consider drive response configuration here, drive dynamical system X and Y. The drive system is autonomous. The response system depends on Y. Now, what's the Lyapunov exponent in the autonomous system is the conditional Lyapunov exponent in the driven system. Conditional means, so in an analog way, like you're writing a perturbation, a small perturbation of that system when it's autonomous, you're also considering a small perturbation here of Y. Now, if you wrote this down from this equation, you would get derivative with respect to the first argument times delta Y, and then with respect to the second argument times the perturbation in X. But conditioning on X means that you're actually removing the second term. That means we're looking at intentionally using something else than the delta Y here, this psi. This is, so to say, a perturbation that is conditioned on the drive of X. That means a perturbation only of Y, but delta X is deliberately set to 0. And this variational equation gives you the conditional Lyapunov exponents. There are as many conditional Lyapunov exponents as there are degrees of freedom of this response system here. And again, the maximum conditional Lyapunov exponent is also called actually a sub-Lyapunov exponent. Both terms are used interchangeably. If the maximum one is negative, that's this contractive stable behavior. And that's linked in this case to the presence of generalized synchronization. That means functional relationship between drive and response of this kind. So what the way you can think of this is you have such a functional relationship, you have such a manifold here, and what the conditional Lyapunov exponent does is it's contracting here in the vertical direction and making sure that all perturbations of y come back to this manifold. The other way around, if this conditional exponent is positive, this here adds degrees of freedom, so it's chaotic by itself, and you see this as a sort of spread. Now, I've intentionally plotted, so these ones are actually not real systems, they are just for illustration. I've intentionally plotted something more wiggly here in the stable case and something more straight in the other case, just to illustrate that counterexample of the case that we might have higher correlation in this situation, despite having an instability or an extra chaos which generates this sort of noise, and might have a lower correlation in the other case where we have a actual strict dependency. Now, this is a famous counterexample. And how can we so experimentally distinguish this? So that's actually the analytical or numerical way, calculating Lyapunov exponents. In experiments, but you can also implement this numerically, you just attach another replica unit. And well, the logic behind that is simple. If there's a functional dependence, if y of t is a function of x, then also y prime is going to be a function of x. I'm assuming now ergodicity, and they're all going to the same attractor. And therefore, y and y prime are going to be the same. So you can unwrap this eventually complicated nonlinear functional relationship between x and y with using this simple trick. And that's also the key to the entire consistency concept, because then you map the nonlinear relationship to the simple linear relationship between y and y prime, so the original anti-replica. And if we have generalized synchronization and our conditional Lyapunov exponent is negative, we see the identity here. Otherwise, if it's positive, we see some deviations of this. So why is that so important to have such a replica test? Well, both in the experiment, it might be the only thing that you can do in order to check for what sort of dependence you have. But also, this dependence might be, in fact, so complicated, and there are examples out there in the literature where the dependence xy is such a, I'm typically using the term nonlinear convolution, so take this with a grain of salt, but it's such a complicated nonlinear dependence that you by no means are able to detect any dependence. So time series would need to be astronomically long in order to see any small signature of mutual information. You can construct such systems. So now coming to consistency. Consistency is actually an extension of that idea of generalized synchronization and the replica test for generalized synchronization. So generalized synchronization, if you look in the literature, it's mostly something that concerned chaotic coupled maps, but hasn't really gone into experimental practice. And so, yeah, without describing the entire historical background, so say how consistency developed across different fields, it's just, we want to get away from a strict functional relationship between a well-defined drive system and a well-defined response system to more something that you have in real-world applications. You might have some information carrying driving signal entering and entering your dynamical system. So there's a particular reason that these things resemble the symbol for a laser diode. So this could be a laser, an electronic system, spin magnetic system, any sort of fast nonlinear experimental system subject to an external driving signal. And well, now consistency just refers to the ability of that system to respond in similar ways when driven repeatedly with that signal. So we repeat the input and we look how much does the output actually agree. And for instance, this here is what we call a completely consistent response. This here is an inconsistent response. And that's actually the second point where consistency is meant to go beyond generalized synchronization. It's supposed to quantify how much of a functional dependence is there, something between 0 and 1. 0 if the output is completely unrelated with the input, and 1 if we have complete consistency. That's in contrast to the generalized synchronization where you actually just speak of the case you either have it or you don't. It's a binary classification, whereas consistency is something in between. Two things to say about this consistency. We're going to go into the measure in detail later. The level of consistency would depend. You see here, for instance, the properties of this driving signal have been slightly altered. So it would depend on the driving signal, but also on the node. That means if you change a parameter of the node, you might transition from low to high consistency or the other way around. But you can also achieve this by changing just the signal amplitude or some properties of the signal. A little bit looking around consistency. So that sort of consistency that I'm speaking here is a concept in dynamical systems, and it's not very widely known. It's a little bit of a niche that I've been working in. As I said, good for experiments and numerics, depends on drive and the system. Has been introduced first in 2004 by Uchida, and Raj Roy also from Maryland was involved. One interesting related concept, and that might have also influenced the arrival of consistency, is what neurosciences have been doing. Here in that science paper from Meinen and Zanovsky, they have been asking the question, when we look at the response of neurons or groups of neurons to external stimuli, what was known by then is that the spiking rate mattered. So to say, there was information encoded in how often actually the spiking, whether there's a lot of activity or little activity, and that you could see a difference in there. But the question was there whether or not the individual spike timing also mattered in the sense of, was it information carrying? Was it involved in some information processing? Or was it just a form of noise where they, so just contributing to the average activity of a particular neuron? And this finding here actually told, yes, there are indications that the spike timing does encode also some little information, which is interesting. Now, there are different layers, obviously, where information is encoded, and that's also some sort of mindset that went into the development of reservoir computing later. So consistency is asking also, of course, that question. Yeah, when you drive the neurons repeatedly, are they fully consistent? Means that even the spike, that they are responding even up to the level of spike timing, or are they only partially consistent? The consistency, this consistency is unrelated. There's also consistency in statistics, which is about the convergence toward a limit. In logic, yeah, of course, that's the naive meaning of consistency. There's dynamic inconsistency in game theory and economics. I looked that up, but don't ask me about that. What consistency is not, there's a dynamic consistency, also very related to ODEs, but that's coming from numerical integration. That means a numerical solution is dynamically consistent with the actual solution of the ODE. And that has nothing to do with this sort of consistency that I'm speaking of. Now, what I mean is consistency in terms of this functional dependency and matching of responses to identical, to repeated inputs. And now we're looking at this in an experiment that's also from a laser experiment. For instance, we need two responses or two repetitions of this experiment. Measure now X original, X replica, and plug it into a Pearson correlation coefficient. As you later see, that's a little bit of an overkill. You don't need to, or actually accounting for an asymmetry. So in this here, that doesn't make sense because it's a highly symmetric situation. If you look, for instance, here at these phase space portraits with a density of original and replica, that's the typical situation that you get. And what the correlation coefficient measures is just how aligned they are. And here, for instance, changing a parameter, we see transitions between low and high consistency. This here is actually an artifact, or it's not an artifact, but it's an effect of measurement noise. If you had the same system in numerical simulation, you would see this go up to almost 1 again. But here it's actually measurement noise that's contributing to this apparently low consistency. So something like this you can observe. To link it with the conditional exponent, or I said sub-Lyapunov exponent is the same concept. Here's the same dependency, again, the consistency correlation and the sub-Lyapunov exponent measured from the same experiment. The interesting thing about this is the fact that the sub-Lyapunov exponent is all the time negative. That means, according to theory, we would say that these systems are in a state of generalized synchronization and should be completely consistent. But apparently that's only a part of the story, and in the experiment there's happening a lot more. In particular, what causes the system to not respond exactly with the functional dependency despite this still negative exponent is that there are fluctuations, the finite time fluctuations of the Lyapunov exponent. So that leads to bubbling and bursting away from this manifold, and that already causes a significant drop. So if this so far was confusing for some of you, that's actually now a good moment to entirely reset and start over, because I'm going to construct the theoretical ideas behind the consistency that I was speaking about. So consider just a black box. Doesn't need to be a dynamical system, could also be something that takes into account intrinsic noise or measurement noise. You just have a black box receiving an input signal u of t and generates an output signal x of t. For now, let's think they're scalar. Important assumptions to soothe a little bit the statisticians when they're looking at what comes in the following is I'm looking at stationary trajectories. I'm looking at systems that are ergodic. So practically in dynamical systems language, there's just one attractor. And arbitrarily long recordings so that I can have perfect statistics, and I'm going to speak only about the asymptotic behavior. And also we can generate an arbitrary number of repetitions of this input signal driving the black box so that we get an entire ensemble of responses, as many as we need. And there's a convention that I also always like to use because it simplifies a lot the formulas. All of these responses are centered to zero mean and unit variance. And in this convention, the consistency correlation looks as simple as this. These angled brackets, I'm using them just as a temporal average, average over time. It's not a scalar product. It's nothing that involves any normalization. Normalization is built in the x of t's. So this is just the time average. So the first thing that we can say, so the fact that I'm taking here two ensembles, one without the prime and one with this prime here, that's just a technical trick. So actually, you can think of just one single ensemble of responses. the first thing where we use ergodicity is the fact that no matter which two responses I correlate, I always get the same result. No? And therefore, I just rewrite it, or using this ergodicity, I rewrite this here now, averaging over all pairs of responses. It's in total m squared of them. And what this allows me to do is to split this sum up here. And this here is then the center of mass of the first ensemble, and this here is the center of mass of the second ensemble. Okay, which I just denote here with this x bar and x bar prime. You may already imagine that when the ensemble is large enough, they might be already very similar. And if we take the limit, actually they are the same. So what we get is something, is an ensemble mean S of t, which is, so to say, the center of mass response of the system for the given input signal. So that's quite useful, because now we split each response linearly in this ensemble mean and deviation eta from this ensemble mean. For those who are very meticulous when it comes to analytics, I'm aware that this here, it's supposed to stand for a noise component, but eta, of course, is not a Greek symbol for n. That should be new, but it's not so nice to read. Now, because of this has some interesting consequences. Firstly, these two things don't correlate. That's one of the consequences. So signal and this noise component, they don't correlate. Two different noise components of two different responses don't correlate. And thus we can split the variances up like this. And also, if we look back here, what the consistency correlation actually is, writing it in these ensemble means, it's just the variance of this ensemble mean over time. So what we here also see is in this limit, the consistency correlation is always positive, and I'm also going to use this term gamma squared for that. Another few remarks on this. This decomposition into a consistent component and an inconsistent component is not necessarily the only decomposition that you can do with your signal. Because if we think more carefully about it, what the ensemble is actually describing is, in the limit of a large ensemble, a probability distribution rho of x and t. So some PDF that depends on time, and which fully describes the response of the system. And our ensemble mean is actually just the first moment of this distribution, whereas all other moments, so to say, the entire distribution also carries consistent information. You could extract other information, so to say, you could define other consistent components out of this distribution. But the fact that we're using here just this linear one is related to the choice of the linear correlation by which we're measuring the consistency. Yeah, for instance, here Jensen's inequality. If we took, for instance, the observations, the squared of all these trajectories, we would get something else than s squared. An interesting Fusarov letter, which in 2010 described this here also as the response in chaotic systems. They also raise this idea, and we're speaking of the Liouville operator, which propagates this probability distribution, and we're also arguing that the leading eigenvalue of this Liouville operator is always negative. That means whereas the microscopic responses are inconsistent, the entire PDF describing the ensemble of responses is practically something that you can consider consistent. And they also discussed the issue of synchronization versus correlation, because that's often also, especially in experimental works, used interchangeably. An interesting observation about this here is it's so far just received 5 citations, and 3 of them is us. but anyway.
The other two are the authors, or?
The other two, one is Uchida, who was also in the consistency, and then one of the Palma crew who worked on this. So that's the entire global circle working on this sort of characterization. Last part of this theory, well, last part of this section, is what else can we say about this? If we know something about the consistency, if we know the consistency correlation, this is this gamma here, we can say what happens, for instance, if we had an arbitrary reference signal, let's say z of t, also normalized according to the convention. It's not entirely arbitrary, so what may be included is any function of the drive, but what is excluded is any function of the individual realizations. So that's how much arbitrary is allowed. And if we now ask what correlations of the output of our system, which is, so say, some realization xm here, with an arbitrary target signal is actually possible, given consistency. And we can straightforward calculate that. So all correlation come from the consistent component. So we strip away the noise component. So we just rewrite this like that. And then all we consider is the magnitude. So the standard deviation of this here is gamma. This here, this correlation is maximized when z of t is just by up to a prefactor equals s of t. So when it's exactly aligned. So that's what we can say about an arbitrary signal without further specifying. And this gives us an interesting relationship, namely that any correlation that we can get is between minus gamma and plus gamma, the square root of the consistency correlation. That means that's how far the output is able to approximate any other signal. And that's relevant for reservoir computing, where the output is actually supposed to approximate some target function. So quick summary reservoir computing. We were all the time speaking about driven dynamical systems, and I'm also using here the same terminology, driving signal u of t, and now this thing, this dynamical system which responds is the reservoir. It's large dynamical system, typically hundreds or thousands degrees of freedom, either in continuous time or discrete time. What else can we say about it without going too deep? Yeah, what's called in reservoir computing the echo state property is, in the consistency jargon, complete consistency, which means a functional relationship of the state of the reservoir with its driving signal. What we do in reservoir computing is we calculate a linear combination of all these degrees of freedom to derive a readout signal y of t. Usually determine this readout vector via ridge regression. So there's a certain target given, so that's where this set of t comes from. And yeah, the readout is supposed to approximate the target as good as possible. And consistency comes into play because consistency, according to what we had before, fundamentally limits, of course, the ability of a reservoir computer to approximate any target function. Yeah, just some more pictures about the reservoir computer. So think of it, it's a system that produces you a bunch of time series. An important characterization of this, we had that at the last time, but this is good to repeat, is the principal component analysis of these responses, because we moved now from a scalar response to a multivariate response. And principal component analysis actually tells us how much these individual degrees of freedom are correlated. And in the reservoir, they're actually they're typically quite correlated, which we see in this huge scale over many orders of magnitude of these principal components. So principal components, for those who are not so familiar with this, are actually just analyzing the covariance matrix of this response and looking at the eigenvectors, and the sigma k squared are the variances of these signals in the characteristic directions. So keep that in mind. Now we jump back to consistency. That's what we did a couple of years ago. Right, it's already a couple of years ago because we started at 18. We can do the replica test with the reservoir, just driving it repeatedly with a with the same signal. So that's here an illustration of this replica test with the reservoir computer. So multiple times here, in this case, exactly twice comes the same driving signal. And the most general case that we can assume is that the responses that we measure at the individual degrees of freedom are slightly different. Now, that could be due to either noise in the reservoir if you have a physical system, or observational measurement noise, or actual chaos in the reservoir because it's a dynamical system. And this is also going to translate to our readout. So that means if there's some degree of noise in these degrees of freedom inside, we're going to also have a certain mismatch here in these different responses in the readout. And the question is now, how do we characterize this multivariate consistency? Naively, we would say, just look at each node individually and measure. So this consistency correlation, again, assuming the same normalization as before here, measure just the consistency correlation for each node separately. Well, fair enough, you get a number of n of these consistency correlations. If we have a readout vector for a certain task, we can measure the consistency in the readout by correlating these here. Okay, which is actually just a special case where, or the node consistencies are actually a special case of the readout consistency when we take a readout that just selects an individual component. Yeah, we measure the individual node consistency. So the most general case is this directional consistency that we get with respect to a certain readout R. So well, let's have a look at this. For instance, here in echo-state networks, that's the standard map of an echo-state network. We can vary the spectral radius, which is something like an internal gain, a main parameter of this reservoir, which generates a transition between a stable regime and a chaotic regime. And here, as a function of the spectral radius, we measure, for instance, the average of these individual node consistencies. The consistency is on the right axis. So 1 is this level. That means it's fully consistent up to a certain point, and then, yeah, that's the so-called edge of chaos. And then consistency breaks down and gets small because there are more and more positively conditional Lyapunov exponents. Yep.
Is that the consistency of the nodes or
yep.
the readout?
That's the individual nodes, and that's the average actually.
Average.
Yep.
Okay.
Because that was just still on the naive approach. Because, yeah. And here, what we're doing a standard task. It's a memory task. So the task of this reservoir is to recall past states of the input, which is the linear. That's what the so-called linear memory task. For each tau, for each lag tau, we get a different readout vector, and we measure the consistency of this readout for each of these memories. So this gives us some curve gamma of tau. Now let's recall the previous identity from the theory. Any correlation, so consider the entire reservoir now as a black box that generates this single scalar readout signal. Any correlation with any signal that this is going to generate must be smaller than the square root of this, namely this gamma. And this is also what we see here. Namely, if we measure the alignment of the readout with the target, this is the solid curve here. It's just the blue and the red, they're just two different configurations, but the solid curve is actually the performance. This is the correlation with the target. And the dashed curve, they are these consistencies. And we see actually that, yeah, this boundary is quite perfectly reached by the performance. Or in other words, the consistency seems to be the limiting factor of the performance here. But what was also surprising is the fact that if we look at the average node consistency, which is something like 0.2, so we were operating around here at that point. The average node consistency is 0.2, but still the consistency levels that we measure here for the at least for these very short legs, it's close to 1. So how do we get this almost perfect consistency out of such a noisy reservoir? That leads to the standard recipe that we are using at the moment. Namely, it's something related to principal component analysis. Also like to acknowledge the nice discussion that we had with Liron and Inge last time. So they're experts in canonical component analysis, and that's a very similar statistical method to what we're employing here. It's about, yeah, well, considering the directionality. So you're not just looking at the individual nodes, but looking at the entire phase space where there are all sorts of angles and linear combinations. That seems to be the key to understand this behavior. I'm going to go quickly through this recipe because it's, well, you just copy that into your favorite programming language, and that's an algorithm to calculate number of consistency levels. You start with a covariance matrix. This has the nice property that it's positive semi-definite, and you can have this eigendecomposition here with just the positive or the non-negative eigenvalues on the diagonals of the sigma squared. Now, from this, you derive a coordinate transformation, which looks like this. We called it something like an isotropy transformation, but statisticians told us they are calling this a sphering transformation because after applying this coordinate transformation, you have unit variance in every direction. So that's what we do. This is the sphere coordinates here, the x tilde after this transformation. Same thing with the replica because we're driving the system twice and recording original and replica. In these normalized coordinates, so this normalization takes over what's in the scalar case, the normalization of the Pearson correlation formula. In these normalized coordinates, we're taking the cross covariance matrix between the original and the replica. And it has also the nice property, so if we take into account that it's a long time series, ergodicity, and writing into the ensemble mean, that this is also a positive semi-definite matrix. So we can express it through the ensemble means like this here. And we can also decompose it again like this. And then on the then the eigenvalues are these positive gamma squares. So just to confuse you entirely, here was a hat. That's for the individual node consistencies. Whereas these ones here, they are, so to say, the holy grail. They are the directional consistencies. And there's also n degrees of freedom. You have n different, n distinct. Oh, I shouldn't have written this like this. So it's, well, yeah, it doesn't matter. So this illustration here shows what it actually does. These ellipses, they encode the standard deviations of the signals that we're employing here for just a two-dimensional system. So this would be the original coordinate x1, and this would be the coordinate x2 of the reservoir. What we had previously, the principal component analysis would give us this object, the black outer ellipse, which is, so to say, the shape of the end of the full response. And within this red inner ellipse, that's, so to say, the consistent part, the consistent component of the response. That means the gap between those, that's the noise or chaos part. And what we just did the slide before with this transformation is we transformed this here, the outer one, into a unit circle. And in this unit circle, we have the desirable property that the inner one has its principal axis exactly where there's the, in this case, here's the maximum correlation, so the maximum ratio between inner and out, and here's the minimum ratio between inner and outer. And if we plotted the complementary part, namely the shape of the inconsistent component, would be an ellipse that shares exactly here the same main axis. And that's not true anymore if we transform this back here in the original coordinates, because what's here, the direction of maximal consistency is slightly off. This principle, because that's just because these main axes are just let's say an artifact of the geometry in which you are looking at it. So they are not the characteristic consistency eigendirections. The consistency eigendirections, they form some non-orthogonal set in the original, but an orthogonal set in the sphered coordinates. And yeah, last but not least, how does this look like? T3 already presented this a couple of months, weeks ago, but by then it was still kind of work in progress, or we just had it submitted, but now it's accepted. And since it's a topic that is quite hard to understand, it's always good to have a little bit of a refresh. It's exactly the application of this sort of formalism of this algorithm to calculate the consistency. So this set of the gamma case, these directional gamma cases, is what we call the consistency spectrum. And here are a couple of these consistency spectra for different echo-state networks. So this is, you consider the ring network, is the standard case of a sparse random network, and the fully connected, just for comparison, to see if there's any specific difference in the consistency of all of these. Sorry, I didn't bother to, so the first row is the ring, the second row is the sparse random, and the third row is the fully connected graph. This column here is for observational noise, that means just additive measurement noise. And this row is for intrinsic noise. And it seems to all reveal the same picture when we have, when we plot this. So this here from 0 to 200 is the index of the, of this eigenvalue of this component. And the different colors here, these different bunches of curves, they are corresponding to different noise levels. So what we always have, and that was the key to understanding this high consistency despite low consistency at the individual nodes, is that there are always a few directions which kind of survive the noise and stick out of it. So there's always a few directions which are strongly noise resilient despite high noise. And on the other end, there are always a few directions which are completely useless because they effectively don't have any signal in them. And the rest is somehow decaying. We can understand this to some extent. Just 5 more minutes. We can understand this to some extent. So I'm recalling now, this is the principal component analysis that we had from a noise-free reservoir. That was the picture that I had before. When we have additive measurement noise, we can actually analytically directly write down what are the consistencies going to be, because the noise variance just adds directly on each component separately, which means we have these noise-free principal components spread over many orders of magnitude. If we add a certain amount of noise, that means some of these components below the noise level, here are 3 different noise levels indicated, some of these components are going to be just covered by this noise level, while others survive. And depending on the noise level, you cover more or less components. So you can imagine if you, so what we get analytically is that the consistencies are just the ratio between the signal variance and the total variance, which is signal plus noise variance. And this is so to say connecting to the previous picture. You can imagine here at this noise level we are covering here the tail, which gives this drop off, and with a higher noise level we're covering more of them, which gives you a larger suppression of the signals, except for the few leading ones which survive the highest noise levels. One thing we also figured out, which is a sensible measure, and that's also analytically directly related to performance, is that when you sum up over this entire spectrum, you get some interesting measure here, this, what you call theta, which we call the consistency capacity. And if we look at this capacity, we see some interesting scaling laws. Namely, if we change the reservoir size, we see that the capacity scales with the square root of the reservoir size. If we change for a fixed size of the reservoir, the noise intensity, we see the capacity scales with the inverse of the noise intensity. Analytically, there's also a change in the scaling expected at sufficiently high noise as soon as all the signal components are covered. This here turns from a -1 to a -2 power law decay. But that's very hard to observe. Yeah, and what this capacity means is actually an effective reservoir size. It's a number between 0 and the number of degrees of freedom of the reservoir that tells us how many degrees of freedom are available for synthesizing a target signal. So we have this scaling here, square root of the size. This is effectively how many are robust to noise. And yeah, finally, if we use this here for rescaling the reservoir size and plotting the performance for a particular task, here is a chaotic time series prediction task. We see that actually the curves of the performance measured by the mean square error all collapse. Now they largely collapse. That means, yeah, this actually confirms the idea of this effective reservoir size. And that's it. So consistency is a tool that goes nicely hand in hand with reservoir computing. So it's all about characterizing and quantifying the response of a driven dynamical system to its input, and to what extent the response of the system is determined by the input. In the consistency theory, we had we've seen that the decomposition in a consistent signal component and an inconsistent noise component is something meaningful that helps, at least in analytics. Consistency defines a limit for any sort of correlation that you measure from the output of your system. Multivariate analysis gives you the consistency spectrum, and the capacity gives you an effective reservoir size that is relevant for performance of the reservoir. And with this, I'd like to thank you. Here are some references. Yeah. Thanks. Not so much over time.
What is dynamical systems in game theory? I'm kidding.
In game theory, as far as I understood, you have a strategy for a future period, and when that period in time arrives, you figure out that strategy is not optimal, and you might implement actually a different strategy at that point in time. That's so it's a dynamic inconsistency in your game strategy, but that's all I know.
When you have you're comparing the performance with the ring network, the sparse network, and the fully connected one.
Performance, yeah.
No, the other figure.
This one?
We just wrote that, yeah.
That's just consistency. Yeah, well, okay.
So A, B, and C are those three networks. What was D and F?
Oh, sorry, A, B, and C here. I should have erased this. They don't correspond.
They're not the networks.
They're not the networks. No. That's the labels from the paper.
But the red, green, and blue is the different noise level? Or?
Yes. Red is lowest noise level, medium, high noise level for all of these figures. First row, ring network. Second row, sparse random. Yep. Okay. Sorry about that.
Yeah, there's a question from Chris. Do you see that, Thomas? I'm going to read the question to you. I feel like
Please read.
You mentioned that inconsistency can be due to actual chaos in the system. Isn't it the case that even chaotic systems are also deterministic? So the question is, if it's actually you said the inconsistency can be due to chaos, but if it's purely deterministic, where does the inconsistency come from?
It comes from not knowing the initial conditions. Think of that black box idea. So you're putting in the input signal u of t, and your system spits something out, but that depends on some initialization in the black box that you don't know. We're ignoring that information.
It always depends on the initial conditions of the reservoir. So
Yes. Mm.
So yes, well, it's, so he's now asked, is it measurement error? It's, well, you can answer. So the follow-up question is it therefore measurement error?
The consistency measure?
So
In which sense?
The
Sorry.
error due the inconsistency for a characteristic system isn't due to measurement error. That's his question, but
No, it's because of the density. It's because of the variability of the chaotic trajectory. You can think about it as the natural invariant density of an autonomous system that describes just the probability of you being somewhere on a chaotic attractor if you didn't know anything further, if you didn't track the initial condition and the time evolution. If you just took a snapshot, if you had a chaotic system and you were just taking a snapshot in time and ask, okay, where am I expecting my trajectory to be? The best guess that you have is the natural invariant density for an autonomous system. But for a driven system, you have a time-dependent density. That's so to say, you have a chaotic attractor which is being modulated, which is moving around in phase space, and therefore it's exactly this uncertainty about the initial conditions, which translates into the probability density that depends on time.
yes.
And that's in that sense, there's no noise involved when you have a purely deterministic system. It's just the uncertainty at one point translating into an uncertainty at a different point.
Yeah, okay. Any other questions? Jack's not there, so he's not asking questions.
No, he's clapping. I thought he was helping me.
I'd be happy about the question from Jack.
Sorry?
I'd be happy about the question from Jack.
Yeah, Jack, where's your question?
Hi, Thomas.
Hi, Jack.
Thanks for the talk. It was very interesting.
Thanks, Jack.
I was just curious. Do you think that this could be used to determine whether systems are causally linked? So here, I guess you sort of assume that, well, that one system is feeding into another. But do you think that you could look at how consistent they are to determine whether they are causally linked at all?
Mm-hmm. Yeah, so guess I know you're pointing at the time series analysis and then trying to infer at causality and infer the causality from there. Yeah, this all takes place at the level of the replica test, where you're able to create already a replica. You assume you have that this system that you're observing is being driven by something, and with the replica test you are not sure if you can use it for inferring causality, because it's an assumption that's behind the entire formalism. Yeah.
Okay. Thank you.
Thought about it.